Is there alien life out there? If so, is there a chance that they're trying to contact us? For many years, the enigmatic question of are we alone in this universe has literally haunted all of us, including physicists, astronomers, and space enthusiasts like you and I. We began working on a lot of theories, equations, and making technological advancements that could help to get us to the bottom of this equation. As we embark on this exploration of the unknown, let's get to the bottom of the theories that exist today. Let's hope that we find a clue if aliens exist by the end of this narrative. At the core of this quest is a simple yet profound molecule, and that's water. Water is the essence of life as we know it. It serves as the beacon for the search for life. Water's role as a universal solvent provides a medium for biochemical reactions to occur. Because of its crucial role in sustaining Earth's diverse biosphere, it makes us look for the same type of molecule elsewhere in the universe. But here comes the question, where can we find these planets? Let's take our solar system as the starting point for our search. From the scorching surface of Mercury and Venus to the icy realms of Neptune, Earth stands as this unique oasis of life. This perfect positioning of the Earth is called the habitable zone or the Goldilocks zone. So what is habitable zone? This is a region around the star where it's neither too hot nor too cold for liquid water to exist. The habitable zone parameters are influenced by the star's characteristics, such as its temperature and size, and by the planet's atmosphere, which can alter the conditions on the surface through greenhouse warming. For instance, Venus, despite lying on the edge of solar system's habitable zone, it experiences a runaway greenhouse effect that makes its surface inhospitable to life as we understand it. But what we've learned recently is that we don't need the habitable zone. Our solar system provides these various other places where life could exist. For example, the icy moons of Jupiter and Saturn. We now have measurements and evidence that Europa and Enceladus have subsurface oceans that have liquid water, and the water is kept liquid by tidal heating. And this is caused by the gravitational tug and pull by the planet. When Cassini flew by Enceladus, it detected hydrogen gas in the plumes that it was able to measure. Together with the presence of silica, this showed and presented evidence that there is substantial hydrothermal activity on the ocean floor. And of course, the recent attention towards Venus with the detection of phosphine and sulfur compounds hints at the possibility of life in extreme environments, further expanding our understanding of habitable conditions. As a result, scientists are now interested to go beyond the habitable zone and look for signs of life in a wide range of other possible areas. We can broadly categorize this into two efforts. One is looking for advanced extraterrestrial intelligence, and two is looking for microbial life or any signs of biological activity. And scientists often use mathematical models to provide us insights into all of these hypotheses. At the core of this is the Drake's equation. The Drake's equation helps us understand the likelihood of finding extraterrestrial life. It is a probabilistic formula to estimate the number of communicative extraterrestrial civilizations in our galaxy. It factors in variables such as the rate of star formation, the fraction of those stars with planetary systems, the number of planets that could potentially support life, and the odds of intelligent life developing. It's more of a framework than a strict predictor. The Drake's equation encourages us to think critically about these various factors that could be influencing our search for alien life. With over 5,500 planets already discovered by telescopes such as Kepler and TESS in the last decade or so, and as we perform analysis of the James Webb Telescope measurements of planet atmospheres, we need updated equations to help guide our search for alien life on these planets. To narrow down the search, a powerful tool was developed, and that's the Seager equation. The Seager equation is a modern complement to Drake's equation. The equation focuses on searching for planets with biosignature gases. What are biosignature gases? These are produced by life that can then accumulate to the atmosphere to levels that can be detected by remote space telescopes. If we find these gases that we can attribute to life, we will still not know if these gases were produced by intelligent life or by simple bacteria. This equation focuses on the observable features that indicate the presence of life, considering the planet's star type, planet size, and atmospheric properties. As in the words of Sarah Seager, if we're lucky and everything turns in our favor, we will be able to infer signs of life on those planets. and maybe we have a shot of finding life within the next decade. Together, these equations represent humanity's first steps towards reaching out into the cosmos, laying the groundwork for a search that spans across both space and time. The evidence of any biological activity is a key indicator of life. The search for alien life isn't just about looking for evolved, intelligent species. Understanding composition of a planet's atmosphere, surface features, chemical signatures, and temporal variations act as biosignatures. And these help scientists assess the potential habitability of exoplanets and prioritize targets for further study in the search for extraterrestrial life. And like I mentioned, to be able to detect these biological activities, we need to be able to measure the compounds that sustain life in the atmosphere of the planet. Exoplanet atmospheric studies are at the forefront of this search. So how does this work? When light from a star passes through its planet's atmosphere, certain wavelengths are observed by the atoms or molecules present in the medium. The remaining light that is transmitted through the medium forms the spectrum, which is a plot of intensity versus wavelength. Each chemical element or molecule has a unique set of absorption lines. These appear as dark lines or dips in the spectrum, which provide information about the chemical composition or physical conditions of the medium, and thereby clues like for oxygen, methane, and other molecules that support biological activity on a planet. There are several upcoming big missions that are aimed at making these observations and measurements in the near future, and these include the launch of next-generation space telescopes that are designed to observe exoplanets in unprecedented detail, and of course mission to Mars, Europa, and Venus that could uncover signs for microbial life. And when it comes to searching for intelligent life outside of our solar system, there is one project that you should know about, and that's called SETI, the Search for Extraterrestrial Intelligence. SETI employs radio telescopes to listen to deliberate signals from extraterrestrial civilizations. And the Drake equation that we talked about not only acts as a theory but provides a scientific basis for the SETI project, transforming the search for alien life from just science fiction to a tangible research-based endeavor. By scanning the cosmos for non-random structured signals, SETI researchers hope to find evidence for technologically advanced species of life. After all of this, the question still haunts us. If the galaxy should be teeming with life, why haven't we found it yet? This is explained best by the Fermi paradox. The paradox highlights the discrepancy between our expectations of a universe teeming with life and the absence of empirical confirmation. This paradox leads us down the path of speculation. Perhaps civilizations have risen long before us, or fallen long before us, or they may rise much later than us, fleeting in the cosmic timeline. Maybe our cosmic timelines and technologies are misaligned. Our signals may be passing like ships in the night. It's conceivable that these vast expanses of space may dilute these messages, in fact stretching time between call and response for centuries. There's another interesting theory called the dark forest theory. The dark forest theory suggests that civilizations may intentionally stay silent to avoid detection by hostile forces. This concept adds another layer of complexity to our search efforts. And in a twist that challenges our perception, maybe these aliens may be walking around us cloaked in technologies that are far beyond our understanding. Each possibility expands the narrative, adding layers of complexity and wonders to this search. But why is this search important, especially to us? Beyond pure scientific curiosity, understanding extraterrestrial life can offer profound insights into our biology, our origins of life, and the potential for self-sustaining planets. It pushes the boundaries of our technology and problem-solving skills, driving innovations that can have wide-ranging applications here on Earth. This is a narrative that binds us together, a story of exploration, and a hope that transcends borders, cultures, and generations. The search for extraterrestrial life is more than a scientific endeavor. It's a reflection of our profound aspirations, a testament to the indomitable spirit of inquiry that defines us as a species. The search for extraterrestrial life is bigger than you and me. So let's challenge ourselves to think bigger, to innovate, and to dream of possibilities beyond our wildest imaginations. If you like this video and want to see more, don't forget to like, share, and subscribe.